Hello everyone. So let's continue our discussion about lecture 3. We solved example 6 in the last part of the lecture. We have several properties of the expectation. In particular, if the function can be splitted, if the function that we want to find the expectation of can be split into additive portions, the first portion of which is dependent on x and the second portion of which is dependent on y. If we can restate the function in this additive format, in that case the expectation of the function, this p-weighted function, can be written as the sum of the individual expectations. Okay, so expectation of the first part of the function plus the expectation of the second part of the function. Now in b part we have a function which can be shown as the product of two random variables, right? So there is a p-weighted function whose arguments are x and y, and then if the function can be shown as the product of these two random variables, the first part of which is completely dependent on x and the second part of which is completely dependent on y, then we can actually find the expectation of this function, of this p-weighted function, as the product of those individual expectations. And the same property carries over to this particular case. Whenever your gx is just x and gy is y, if that is the case, and given that you have independent structure, then the expectation of this product is just the product of these expectations. But pay attention to these facts. You have to make assumption that x and y random variables, they are completely independent of each other. Okay, here we have mean vector. Mean vector is just the expectation applied to the vector. And then we have second moment matrix, that is the expectation of x times x transpose. I don't want to spend too much time on them. They're just definitions. Now let's move to moment generated functions in p-weighted and multivariate case. So we're supposing that you have two random variables, they have joint density that exists. If that is the case, then the expectation of this function t1 times t2 times y is going to be the joint moment generating function of these two random variables. If you remember, in the univariate case, let me use zooming a bit. Okay, in univariate case, if you remember, we got this property. We said that the moment generating function of random variable x was equal to the expectation of e to power t1 times x. That was the moment generating function. But if you want to extend this analysis to p-weighted case, then moment generating function of xy will depend on two parameters, t1 and t2, and that can be found by the expectation of e to power t1 times x plus t2 times y. Okay, now let's apply this property. Suppose we have, let's look at example 7. Let me copy that. Okay. Suppose that we have a joint density fxy xy equal to e to power minus y, in case if x is in between 0 and positive infinity, and 0 if else. Okay, so if that is the case, to find the moment generated function, so maybe I should write example example 7. Just a minute. Oops. Wait a minute, please. So let me say this is example 7, and we have join PDF. Which is nothing but e to the power minus y given this and 0 otherwise. So now to find the moment generating function, join moment generating function, so let's say xy t1 t2. This is nothing but the expectation of this function e to the power t1 x plus t2y. We are supposing that t1 and t2 they're positive and less than 1. Actually, we'll suppose that in this particular example we'll see that we have to put condition, constraint that t1 plus t2 is less than 1 and they're positive values. Okay, so how we do that, obviously it can be found by the joint integration, but pay attention to these boundaries. X should be less than y all the time. Okay, so we can do it in two ways. We can say, first we can say that x runs from 0 to y, and as I mentioned already, the outer integral should have numerical boundaries. So the other one, the y is going to run from 0 to positive infinity. And then this is the integral that you have to evaluate. E to the power minus y times the function whose expectation we want to find. t1x plus t2y. And then gx, first we are integrating with respect to x, and then with respect to y. So this can be rewritten as, if you want to change the order of integration, if you want to integrate with respect to x first, then you have to be careful because of this dependent structure in the intervals where y and x is defined. You have to be careful. So when you are integrating with respect to, if you want to integrate with respect to y first, then you have to say that y is running from x to, positive infinity, isn't it? And then x itself is changing between 0 and positive infinity. So you will see that if you do these two integrals, both of them are going to give you the same result. Here we have to integrate with respect to y first and then with respect to x. So, okay. So I do it in this way. Obviously we can rewrite it as so if you integrate with respect to y, what you're going to receive is you're going to receive e to the power t1 x plus t2 minus 1 times y over t2 minus 1, right? And then you are going to evaluate this integral between 0 and between x and positive infinity. And then after that you have to integrate with respect to x. Okay, so if you do that, what you're going to receive, so let's plug upper boundary. If you plug upper boundary for x, you're going to receive, for y actually, and supposing that t2 and t1, both of them are less than 1, so this guy is going to be negative. Because this coefficient is negative, then negative times positive infinity is going to give you negative infinity, and e to power negative infinity is just 0. So this is going to be, if you plug positive infinity, in the limit it will be 0 minus, if you plug x, you're going to receive e to power t1 x plus t2 minus 1 x, and everything divided by t2 minus 1. Then we are going to integrate with respect to x. Okay. So what we can do is, we know that t2 is less than 1. So if you switch the places, then you're going to receive, the order of t2 and 1. You can get rid of the negative sign. So we can say that this is from 0 to positive infinity. E to power, let me simplify it a bit, t1 plus t2 minus 1 times x, or 1 minus t2, and integral with respect to x. And if you do that, you're going to receive e to power t1 plus t2 minus 1 times x divided by 1 minus t2 times t2 plus t1 minus 1, and you have to integrate them within 0 and positive infinity. If you do that, so if you plug positive infinity, we know that we have to impose the condition that this k here, is negative. Otherwise, the moment generator function cannot exist. Okay, so we suppose that t1, t2, they are positive values, but they're less than 1. Okay, so maybe I should say t1 plus t2 is, they're less than 1, and each of them are positive. They're also, t2 is also positive. Just a minute. So if you have these conditions, so plugging positive infinity here is going to give you 0 minus, and if you plug 0 instead of x, you're going to receive 1 over 1 minus t2 times t2 minus t2 plus t1 minus 1. Okay, and then if you go further, what you can do is, if you want to get rid of this negative sign, we can apply the same intuition. We know that, and this k here is a negative value, so to get rid of this, this negative sign here, you can say that, so it's going to be, it's equal to 1 over 1 minus t2 times 1 minus t1 minus t2, and that's all. That is the joint moment generating function. Now let me see if we have another question here. Okay, so we have to find the individual, like marginal moment generating functions, right? Is it the case? No. Oh yeah. So we have to get individual, like moment generating function of the marginal distribution of x and y. That is easy. Once you have it, according to the property here, look at this property. Let me see. So just, it's here. Let me zoom it in a bit. You can see that. So if you have a joint marginal, moment generated function, by setting t2 to 0, you're going to receive the moment generating function for x only, yes, for the marginal probability density function of x. And if you set t1 to 0, you take the joint moment generated function and set t1 to 0, and then you are receiving the moment generating function for the marginal probability density function of y. Okay, that is how it works. Okay. So here we have our marginal, like our moment generating function, which is what? Which is so t1, t2, that is nothing but 1 over 1 minus t2 times 1 over 1 minus t1 minus t2. And this implies that if you want to find the moment generating function of x, the marginal PDF of x, then just set t2 to 0. Yes. So if you do that, you're going to receive 1 over 1 minus t1, right? So by the same token, we can find moment generating function of y, which can be found in this way. You can say that if I set t1 to 0, then this is going to be the moment generating function of the marginal PDF of y, which is 1 over 1 minus t2 times 1 over 1 minus t2, which is 1 over 1 minus t2 square. That's all. Okay. Now let's move on. So here we have some theorem. It is telling you that this is alternative definition of the independence. We know that the independence is this. The independence is, two random variables are independent given, if the joint density can be shown as the product of marginal densities, then we say that x and y, these two random variables, they are independent. The alternative definition is about the moment generating function. So if the joint moment generating function can be written as the product of the individual moment generating functions, then it means that the two random variables are actually independent. Now let's solve one more example. Example 8. We have a joint PDF and we have to find if x and y are independent. You can use either this, either PDF way or, moment generated function way of doing that. Okay, so let me copy this question. Let me write that this is example 8. Example 8 is telling you that you have joint density which equals to x plus y on the condition that both of these guys are within 0, 1, right? And 0 else. So we have to say that. So we need to find the marginal densities, meaning we need to find fxx. And we know that you can find it using the integration with respect to y. So fxx is always equal to, usually we have to do it from minus infinity to positive infinity, obviously. Maybe I have to write it more formally. I should say that this is equal to the joint density integrated with respect to y. And here, because y changes only within 0, 1 interval, I can change the boundaries of the integral. So this is x plus y and dy. If you do that, you're going to receive xy plus y squared over 2 evaluated within this interval. and that gives you x plus 1 over 2. Okay, so due to symmetricity, I don't need to make any integral calculation. I know that f by y is going to be equal to y plus 1 over 2. So now what we have to do is we have to check whether the joint density, I'm always forgetting to add this guy here, xy in the subscript, but that is not really important. Yeah, so I have to show that this can be shown as the product of these two marginal densities, but it is actually not the case. In this particular case, this implies independence. But here, what we see here, so x plus 1 over 2, this is the marginal density of x, times y plus 1 over 2. That does not give us x plus y. Therefore, so this implies that random variable x and random variable y are actually dependent. Okay, dependent. Okay, great. Now let's move on. Okay, here we have to go back. Transformation of random variables. So the same idea. I missed one question here. Example 9. We have mutually independent random variables. Pay attention to that fact. And we know that if you have independence, then the joint PDF can be shown as the product of the marginal PDFs. And that makes our lives easier. So each of them has this kind of probability density function, and all of them are defined within 0-1 interval. That's really easy case. Now we have to find the joint PDF. It's kind of simple, and then we have to calculate this probability. Yeah, here, example 9. So I know that fxx is equal to 2x if x isn't within this boundary, and 0 if else. And the same goes for fy, the second random variable, or here actually it's fx1, x2, x3. So maybe it's x1. So the same is going to hold for x2 and x3. So if that is the case, and given independence of x1, x2, and x3, if they're mutually independent, then I can say that f x1, x2, x3 is actually equal to 2 times x1 times 2 times x2 times 2 times x3, which is equal to 8 times x1, x2, and x3. And here I have to make sure that, I have to probably say that if all of these guys, if xi is between 0 and 1, for all x's, for all i's which are equal to 1, 2, and 3. Okay, so for x1, x2, and x3, all of them should be, within 0-1 interval. And after that, it's very easy to calculate the probabilities. We know that, right? So we have to find the probability that x1 is less than 0.5, and x2 is less than 0.5, and x3 is less than 0.5. To evaluate this probability, you have to use triple integral from 0 to 0.5, and all of these guys, the order of integration actually can be easily changed in this case, because the intervals of x1, x2, x3, they are kind of not depending on each other. Here we have 8x1, x2, x3. If you do that, you're going to receive 8 times x1 squared over 2 x2 x3 evaluated between 0 and 0.5. And then if you do that, you're going to receive 4 times 0.5, that is equal to 2, right? So actually 4 times 0.5 square x2 x3, and then I have to integrate with respect to x2 and x3. Then if I go further, it's going to be let me delete this part. So it's going to be 4 times 0.5 square times x2 square over 2 x3 evaluated within this interval, then integrate with respect to x3. And if I do that, I'm going to receive 4 times 0.5 square times actually 2 times now, 2 times 0.5 square times 0.5 square, which gives me actually 0.5 to the power 4 x dx3. And if I do that, I receive 2 times 0.5 to the power 4 x3 evaluated between 0 and 0.5, and that is going to give me you know, yeah, here here I missed x3, I'm sorry. So it's going to give me x3 square over 2 again. So I'm going to receive I'll receive what? I'll receive 0.5, because 2's cancel each other out. I'll receive 0.5 to power 6, okay, or 1 over 2 to power 6. Now let's move to transformation of variables. We have already done it for the univariate case. I mean, the same ideas are applying here. The only difference is that here, instead of, you're evaluating the density, joint density, at the inverse function, and what else? Here, instead of absolute value of the derivative, you are multiplying by the determinant of the absolute value of actually you are multiplying with the absolute value of the determinant of the Jacobian, okay, Jacobian matrix. And what Jacobian matrix is, it's basically you have like two functions, h1 and h2. So this is basically the matrix of the first derivatives. You take the derivative of the first function with respect to y1, the first argument, the same function's derivative with respect to the second argument, and so on and so forth. Okay, that's kind of straightforward. Okay, so that is probably, that is the only difference. So now let's look at example 10. In example 10 we have, let me copy that again. Okay, we have, this is example 10. In example 10 we have joint density. Probably I have, let me do it this way. Okay, we have the joint density, which is equal to 10 times x1, x2, and x is defined, the interval of x's are defined this way. Okay, and what else? We suppose that y1 is equal to x1 over x2, and y2 is equal to x2 all the time. So our purpose here is to get the inverse function, meaning that we want to get the inverses. So you can call it g minus 1, y1, y2, and so g1 and g2. You have two functions now. g2 minus 1 expressed in terms of y1 and y2. Okay, so what are those functions? Look at this property. Here x2, to express x2 in terms of y2 is very easy. You just say that. So x2 is equal to y2, that's all. Okay, then if this is the case, it implies that y1 is equal to x1 over y2, right? We just plug for x2, and then that is going to imply that x1 is nothing but the product of these two guys, right? So we have two inverse functions. One is here, and the second is here, isn't it? Great. Now, second thing, we have to evaluate the joint PDF at the inverse function values. Meaning, take the x1, x2, evaluate them at g1 minus 1, y1, y2, and g minus 1, the second function, which has arguments y1 and y2. So if that is the case, we know that this is the PDF, the joint PDF is just 10x1, x2. So this is going to be equal to 10 times, instead of x1 we plug y1, y2, times, instead of x2 we plug y2. So if we don't know that yet, 0 if else, right? Obviously I can rewrite it as 10 times y squared. Great. And third, I have to get the Jacobian. So Jacobian is, so the first function's derivative, the first function is here. Let's call it first. This is second. So the first function's derivative with respect to y1, the first variable, is going to give us y2. So if you take the derivative of the same function with respect to y2, the second variable, you're going to receive y1. Now let's move to the second function. The second function's derivative with respect to y1 is 0. The second function's derivative with respect to y2 is just 1. So this is going to be your Jacobian matrix. Now, if you want to find the determinant of that, and actually, determinant of Jacobian is going to give us what? It's going to give us y2 minus, 0, right? Okay. And obviously, if you take the absolute value of this Jacobian derivative determinant, that is going to give you y2 itself, right? Positive. Actually, this is actually capital thing. Okay. So now we are ready to go. What we have to do is we just have to multiply the second animal, the animal that we have found in the second step, which is this guy, by the animal which we have found in the step 3, meaning the thing in the green box should be multiplied by the thing in the blue box. So it's very easy, right? You can say that f x1 x2 f y1 y2 actually is actually equal to 10 times, so this animal, let's take this animal, 10 times y1 times y2 squared times y2, which is making it as y cubed, if question marks, okay, and 0 if else. Now let's understand what we have for these question marks, because we have to define the interval where y1 and y2 are defined. We know that x1 should always be less than x2. Yeah. And what happens if x1 is less than x2? What happens to y1 and y2? Okay. Now let's look at that. So we know that this is probably, so this is 5th step intervals. How do we define that? Okay. So if this is the case, we can say that, so we have several cases. So x1 is greater than 0, right? So what is x1? This implies that y1, y2 is actually greater than 0. Now you might have two cases here, actually. You see, y2 might be positive. You might have both negative cases, and both of these guys negative and both of these guys positive, right? So you might have this, both negative or both positive, both y1 and y2 positive, because in both cases this condition is going to be satisfied, isn't it? This condition is going to be satisfied. But we say that y2 cannot be positive. It can be negative actually, because y2 is equal to x2, and that is always positive, right? So it means that 0 less than x1 implies y1, y2, and both positive. Maybe I should say. And here I should add 0 x2 and which is equal to y2. So these two things jointly imply that zero is y1 times y2 is greater than 0, and y1 is positive, y2 is positive. Okay. And then we know that, this is the first part, we know that Now let's move to the second part of this. We talked about this, now let's move to this relationship. x1 is less than x2. This implies that, now plug for x1. What is x1? x1 is just multiplication, y1 times y2, isn't it? And plug for x2. x2 is just y2, isn't it? So it means that, this implies that, actually, y1 is less than 1. Yes. Now let's move to the third part. Third part tells you that x2 is less than 1. That implies that y2, because x2 is exactly equal to y2 all the time, y2 is less than 1. So that also implies that y2 is also less than 1. So in this case, what we say, we could not actually see any dependence, right? We could not see any dependence, on the intervals of y1 and y2, meaning that although this interval of x's, they were dependent on each other, we had a condition that x1 should always be less than x2, and both of them should be less than, within 0-1 interval. But we don't see that constraint on y's, y1 and y2. So it means that y is going to be defined within 0-1 interval, and y2 is also going to be defined within 0-1. Okay, so we can now say that f y1, y2 is actually equal to 10 times y1 times y2 cube if y1 is within 0-1 and y2 is within 0-1. And 0 if else. That is all. Yeah, we can obviously extend this analysis to multivariate case. Here we have example 11, but I want to skip this because it is going to take a bit of time, but the logic is the same. Logic is going to be the same. So this is the end of the lecture 3 about multiple random variables. Okay, so see you in the next lecture.